welcome back to my channel. So we continue with the crystal field theory in part 2 here. Alright, so we have stopped at where we have the splitting between the 5 orbitals, where it actually formed the T2G and also EG. Okay, we have what we call here, this is level T2G. It actually has lower energy or low energy, and then we have a level where we have what we call EG with high energy. So in this T2G we have 3 orbitals. They are dxy, dxz, and also dyz. Why all of these 3 orbitals are actually in low energy level? Because all the orbitals, okay, lie between the ligand, repulsion become weaker. So as you can see here, the dxy, the orbitals actually lie between the x and also y axis, and then that's why we call it as dxy. And then we have dxz. Okay, the orbitals, okay, actually lie between the x and also z. The same goes to the other orbitals. And then the dyz, okay, the orbitals actually lie between the between the z and also y or orbitals. Okay, so what happened here? All these 3 orbitals are having weaker repulsion. And then what about the EG level, where they have high energy? So we have the dx squared minus y squared and the dz squared. Okay, so all of these orbitals actually lie directly in line with the approaching ligand. So what happened here? The repulsion become stronger. So for example, here we have the dx squared minus y squared, where the orbital itself, okay, lie in line or lie on the what we call x and also y axis. So we have x here and also y axis. That's why this we call it as dx squared minus y squared. And then we have the dz squared, where we have the z axis, okay, where actually these orbitals lie on the z or z axis. Okay, so this is where we have a weaker repulsion, okay, for the T2G, and also we have stronger repulsion, okay, for the EG. And then so this is what happen when you have an octahedral field of ligand. So here this is where we have the d orbitals in free ion, okay, in free ion. And then the average potential energy of the 3d orbitals raised in octahedral ligand field. Okay, so this is the free ion, and this is where we have, or we complex the metal with the ligand. And then here the interaction between metal and also ligand will give what we call crystal field effect, where we have the orbital splitting. Okay, orbital splitting. These 5 orbitals, okay, the d orbital splitting here will form or will have the T2G and also the EG. Right, and then the difference between the T2G and also EG, this is what we call the delta. So what is the delta? Delta is the splitting energy. Okay, the splitting energy or the difference energy between the T2G and also EG, this is what we call the splitting energy. And then this is the diagram for the 3d orbital splitting in octahedral ligand field. Okay. So this is another example for the octahedral coordination compound or octahedral geometry here. We have isolated transition metal atom and then we react with ligand. Okay. So we have the Lewis acid and also Lewis base. And what happened here, we have the crystal splitting effect, the effect here, right? The splitting effect. So these 5 orbitals will split into 2 levels. Okay, first one is the T2G, lower energy, and also higher energy, where the EG, we call it as EG. For the T2G, we have dxy, dyz, dxz, and EG, we have dx squared minus y squared and also dz squared. So this is a general splitting diagram for octahedral complex. So when you are requested to draw CFSE diagram, so you need to have this. First thing, you need to have energy, and then you need to show the isolated metal or isolated transition metal atoms, and also you need to show the splitting of this energy. And then last but not least, you need to show here, okay, the delta. Okay, right. And then so this delta or the crystal field splitting energy is actually the energy difference between two sides of the d orbitals in metal atom when ligands are present. So here you need to show the energy difference between the T2G and also the EG. Alright, and then for here we have the d electron to ligand electron repulsion affect the d orbital energy levels. So when you have the free metal ion, and then you have the interaction between metal and also ligand, these 5 orbital will start to split, and here it will form this kind of diagram, and the dz squared and the dx squared minus y squared orbitals point at the ligands and have higher energies than other d electrons because of the location of the orbital itself, right? And then you need to show the crystal field splitting energy. So how to differentiate? Okay, which one has higher energy, which one has lower splitting energy? Okay, how to differentiate? First one is the types of ligands. Okay, different ligands will create different splitting energy or different delta. Okay, here. So we have 2 types of ligands. The first one is the weak field ligands, or we call it as weak ligand. And then we have strong field ligands, or you can call it as strong ligands. Okay, so if most of the time, if you have weak field ligands, usually they will have smaller value of the delta here. And if you have a strong field ligand or strong ligands, most of the time this delta will have higher value. Okay, why? Okay, here, for example, here we have H2O. This is one example of the weak ligand. And then another example here, we have cyanide. This is one example for strong ligand. So in this case, okay, how to determine that this one other than types of ligand? Okay, so if you have the weak ligand and also strong ligand, what happened here? Most of the time, the weak ligand will give you what we call, this is small energy, this is what we call high spin. Okay, why? Because it has smaller energy in here. If you have a strong ataupun or a large energy gap here, right? So this is most of the time we call it as low spin complex. low spin complex, and this is high spin complex. Okay, right. So here the chromium here is the 3d4. Okay, so this is the chromium 2 plus. Okay, and then this is negative 6. So this is also chromium 2 plus. Okay, with the 3d4. Okay, 3d4. But okay, if you have the high spin complex, usually they will become high spin complex, and when you have a smaller gap here or smaller energy, okay, you need to fill up, okay, 1, 2, 3, and it can jump to higher energy because we have a small gap of this energy. And if you have a larger gap, okay, or you have the low spin complex, you need to fill up the electrons 1, 2, 3, because this complex has higher energy here. Okay, right? So it cannot one electron from this cannot easily jump to the higher energy because of the large energy gap here, and it will start to fill up at the lower energy. Okay, that's why this one we call it as high spin complex, and this one we call it as low spin complex. Okay, so for the low spin complex, you need to add on you need to fill up all the electrons at the lower energy first, and then you can continue with the second one, okay, or the second level of this energy. But for the high spin complex, the electrons can easily jump to higher energy because, or to the higher level here, e.g. because of the small gap here. Alright, then okay, so we have a smaller splitting energy because this is where we have the weak field ligand, and then here larger splitting energy. For example, here we have strong field ligand cyanide. Okay, then the magnitude of the delta, okay, actually depend on 3 factors. Okay, first one, it actually depends on oxidation state of metal ion. The higher the oxidation state, it will produce large value of delta. And second one, it depends on nature of metal ion. Metals further down the periodic table usually produce large delta. And then last but not least, third one depends on the types of ligands. Okay, a strong field ligand usually will produce a large delta, while for the weak field ligand, it will produce a small delta. Okay, for example, here we have manganese 2 plus. Okay, manganese 2 plus here, okay, with the electron configuration of Ar3d5. Okay, Ar3d5. So, alright, Ar3d5. So for the first one, okay, this is the free manganese 2 plus ion. You have 5 electron in the d orbital. Okay, let's say we have 2 situations here. This manganese is actually reacted with water, weak ligand, and then we have here C, the complex C here. We have manganese react with a cyanide. Okay, and then here, from here we have, this is the also manganese 2 plus, and this is also manganese 2 plus. But the main difference of these two between B and also C is the type of ligand. Okay, so first one here, this is H2O, weak ligand. Okay, weak ligand, and then here we have strong ligand. Okay, weak ligand usually will form a high spin complex, while for the strong ligand usually it will form low spin complex. So when you have weak ligand, the most of the time the delta here will become smaller, while if you have the presence of strong ligand, usually it will form large value of delta. So this is 3d5, so you need to fill up singly 1, 2, 3, and then because this gap is small, okay, another 2 of electron can jump to higher value or higher energy level. But in this C complex, okay, right, because you have a strong ligand, the presence of strong ligand, what happened here, you need to fill up 1, 2, 3, and because of this we have high energy, and then it is not easy for this electron, for these two electrons to jump to higher level, so they start to pair up, one here and also one here, right? So this is where we have the high spin, and this is where we have the low spin complex. Okay, high spin complex and low spin complex. Okay, just because we have two different types of ligands, right? So here we have small splitting, take less energy for the d electron to jump, and then d remain unpaired. And then second one, right, large energy of large splitting energy here, and then take more energy to jump to Eg and pair up. So okay, so and then less electron unpaired in the complex ions. Right, then here, this is the crystal field splitting actually can also account for magnetic properties in terms of high and also low spin complexes. If you have weak field ligands, usually it will lead to high spin paramagnetic system, and also if you have strong field ligands, usually they will lead to low spin diamagnetic system. But in this situation, you need to count the d electron first. Okay, alright. So here, okay, this is for example here we have cobalt. Okay, this is cobalt where we have 2, 4, 6. Okay, 3d6. This is cobalt with Ar 3d6. So the cobalt here is cobalt 3+. Okay, so here we have fluorine. Okay, fluorine is one of the weak field ligand, and cyanide one of example of the strong field ligand. Okay, so what happened here, okay, this how to draw the diagram. You need to have the energy. Okay, this is the Eg, this is the T2G, right? Eg and also T2G. Okay, so you can fill up this 6 electron, 1, 2, 3, 4, 5, and also 6. Why? Because we have a small gap or small value of splitting energy here. While for this second situation, we have also 6 electrons. So you need to fill up singly 1, 2, 3, but it is difficult to jump to a higher value. Okay, and then what happened here, another 3 electrons will pair up with here, here, and also here, right? So for the first case, it will form high spin complex because of the small energy here, and then second case here, it will form a small or low spin energy because, or sorry, low spin complex because of the large gap between here, the T2G and also Eg. Right, other than that, this is a summary, okay, or and also examples for you to refer for the orbital diagrams of high spin and also low spin octahedral complexes, where we have the start from the D1 until the D9, okay, the D1 and the D9, and then you can see here we have the difference between the high spin and also low spin complexes based on the types of ligands. And then I also give you the high spin complexes, no need to pair up, especially for the D1, D2 and D3. And then the high spin complexes, because of the T2G and also EG almost fill, for example for the D8 and also D9. And also I have also include here I have also include the D4, D5, D6 and also D7 for your reference. So I think that's all for this part 2. So if you like this video, please give a comment and then subscribe my channel. So I'll see you guys in part 3. Bye!